The universe is a place of staggering beauty and immense scale. We look up at the night sky and see a serene canvas of twinkling lights, a peaceful emptiness stretching into infinity. But this stillness is an illusion. Out there, in the vast, silent dark, are objects of such power and violence that they defy our everyday comprehension. They are the ghosts of long-dead stars, the remnants of cosmic cataclysms. Imagine an object so dense that a single teaspoon of it would weigh more than all of humanity combined. An object spinning hundreds of times every second, a lighthouse of deadly radiation sweeping across the galaxy. This isn't science fiction, this is a neutron star. What if one of these cosmic monsters were to wander into our quiet corner of the universe? What if its path brought it close, perilously close, to our own small blue world? It's a journey that begins with a subtle disturbance, a whisper in the gravitational fabric of our solar system, but it would end in a symphony of unimaginable destruction. To understand a neutron star, you first have to understand how a star dies. Think of a massive star, one many times larger than our own sun. For millions of years, it lives a brilliant life, a gigantic nuclear furnace fusing hydrogen into helium. This fusion process creates an incredible outward push, a constant explosion that is always trying to tear the star apart. But the star's own immense gravity provides the opposing force. For most of its life, these two forces are in a perfect, delicate balance. But this cosmic balancing act cannot last forever. Eventually, the star runs out of fuel for its nuclear furnace. In a fraction of a second, the star's core collapses under its own colossal weight. This collapse triggers a spectacular explosion known as a supernova. While the outer layers are flung into the cosmos, the star's core continues to collapse, leaving behind only a sea of tightly packed neutrons. A typical neutron star is only about 12 miles or 20 kilometers in diameter. You could drive across it in less than half an hour. It's a celestial object of immense power that could fit comfortably inside the boundaries of a major city. This leads to a density that is almost impossible to imagine. A single sugar cube's worth of neutron star material would have a mass of about 100 million tons. That's the equivalent weight of every single person on Earth. The gravity on the surface of a neutron star is about 200 billion times stronger than Earth's gravity. Many neutron stars spin hundreds of times per second, faster than the blades of a kitchen blender. The magnetic fields of neutron stars are the strongest in the universe, trillions of times more powerful than Earth's. This rapid rotation, combined with their powerful magnetic fields, can turn them into cosmic lighthouses called pulsars. Our story begins with the neutron star still impossibly far away, on the outer fringes of our solar system. At this vast distance, we wouldn't be able to see it with any conventional telescope. The only way our astronomers might detect it is through its radio beams. As it enters the Kuiper belt, the neutron star's gravity would act like a cosmic shepherd, stirring up this tranquil region. Some comets would be flung out of the solar system entirely, others pulled inward toward Earth. Back on Earth, astronomers would observe an unprecedented meteor shower lasting for months, then years. The night sky would be filled with shooting stars, a beautiful but deeply unsettling sight. As the neutron star crosses the orbit of Saturn and Jupiter, its gravitational influence becomes impossible to ignore. Jupiter would find itself in a gravitational tug-of-war with an object far smaller but immensely more massive. Earth's path around the sun would be pulled into a new, more erratic path. Summers could become scorchingly hot as we are pulled closer to the sun, while winters could become unimaginably cold as we are dragged further away. The moon would be wrenched from its familiar path. It might be pulled into a much closer orbit, leading to catastrophic tides, or worse, stripped away from Earth's gravity altogether. The immense tidal forces would start to stretch and deform the planet itself, generating enormous stress within Earth's tectonic plates, leading to a dramatic increase in earthquakes and volcanic activity. As the neutron star draws nearer, the most dramatic consequence will be what happens to our oceans. The gravity would create a monstrous wave, a global bulge of water thousands of feet high. A wall of water, miles high, would sweep across the continents. Coastal cities like New York, Tokyo, and London would vanish in an instant, completely submerged. The wave would scour the land down to bedrock, erasing every sign of human civilization. The friction of this colossal tide would generate immense heat. The oceans would literally start to boil. The atmosphere would become a choking, steamy soup, unbreathable for any form of life. The solid body of Earth would undergo violent transformation. The tectonic plates would be torn apart, massive rifts would open up, spewing rivers of magma. The entire surface would become a sea of lava. The planet's magnetic field would falter and collapse. Without this shield, radiation would slam directly into our atmosphere, stripping the air away until our planet is left as a barren, airless rock. At its closest approach, the neutron star could rip a chunk of material directly from our planet. A stream of molten rock and iron would be siphoned off, flowing through space like a river of fire. The neutron star leaves behind a scene of utter devastation, a solar system scarred and reconfigured. The beautiful, orderly dance of the planets is gone, some planets thrown into new orbits, others ejected entirely. Earth, if it survived, would be unrecognizable, tidally locked to the sun, with one side perpetually baked and the other frozen. The atmosphere gone, oceans boiled away, a silent, sterile world. The passing of the neutron star serves as a profound lesson about the universe. It reminds us that the stability we take for granted is not guaranteed. Our solar system is a tiny, peaceful island in a vast and sometimes violent cosmic ocean. So, why do we imagine such terrifying cosmic events? It's because this kind of grand cosmic thinking is at the very heart of human curiosity. When we look up at the stars, we're exploring the fundamental laws of nature. The same forces that could tear our world apart forged the iron in our blood in the heart of a dying star. We are, in a very real sense, made of stardust, and the story of the universe is our story. The chances of a neutron star ever coming near Earth are practically zero. We are safe. But the universe is filled with wonders just as strange and powerful. These are invitations to be curious. And so, we should keep looking up. We should keep building bigger telescopes, asking the biggest questions we can think of. The universe is a place of infinite possibility and breathtaking wonder, and our journey to understand it has only just begun.